Today, I'm going to be talking about building enclosure problems with kind of a focus on healthcare facilities. I've been a building enclosure consultant for the past 15 years, and contrary to what Kristen says, I don't know everything, but 15 years is a lot of experience. So hopefully I can show you all something you haven't seen before. All right, so we got 5 high points that I want to talk about today. The first is going to be about high performance roofing. Then we're going to move on to building expansion joints, otherwise known as seismic joints. We're going to talk about moisture vapor diffusion through building walls. Then talk about some struggles that the industry seems to have with storefront window flashings, and finish it off with the ubiquitous sheet metal flashings and sealant failures. So let's go ahead and start with high performance roofing. Currently in our industry, certainly around in Indianapolis, the low slope roofs, the market is just absolutely dominated by single ply roofs, which makes sense. They're relatively low cost, they're quick to install, but they have a poor performance history. A number of years back, they did a very large survey of hundreds of building facility managers, and they found that the typical lifespan of your regular TPO or EPDM single ply roof over insulation was only about 14 years. Meanwhile, let's realize that a lot of these roofs carry 20-year warranties, but the industry just is not delivering. Now, hospitals and healthcare facilities are a little bit unique. They have very low tolerance for leaks. It's not like a leak in an office building above the receptionist desk is going to put someone's life at risk, whereas in a hospital, that absolutely can happen if someone is immunocompromised and there's mold in the walls. In addition, not all the time, but some of the time, the healthcare facility roofs have some additional excess structural capacity. In addition, a lot of those roofs have a concrete deck. And I want to look at those specifically right now because there's a real opportunity to do something a lot better than what we've been doing. And this is what's known as a protected membrane roof or an inverted membrane roof assembly. Now, we didn't come up with this. This has been around for way before I was born. And it's a pretty simple idea. You have ballast on top, some sort of filter fabric to keep the ballast where it is. Insulation beneath the filter fabric, some sort of drainage medium, the waterproofing, and a concrete deck. Now, I want to point out 2 things here. First and foremost, you'll note that the waterproofing is beneath the insulation. As a result, that insulation needs to be something that's moisture tolerant because it's going to be getting wet every single time it rains. And I also want to note that here I'm specifically talking about concrete decks. While you can do a PMR or an IRMA over a metal deck, you sometimes lose some of the real benefits from doing an IRMA when it's a metal deck because of some things we'll get into in a minute. But when speaking about healthcare facilities, I want to focus on this sort of assembly. So this right here is actually a picture I took just last week. It's above occupied space, and it is an IRMA assembly. I am standing on the waterproofing that is on top of a concrete deck. It ties in the curtain wall on either side. But what happens next is we come in with XPS insulation, filter fabric, and in this case, ballast, which is pedestal pavers. This is a very good roof. PMRs are arguably the highest performing roofs available for low slope roofs. And that's for a number of different reasons. The first is easiest, it's the longer service life. You can easily get 30 years out of a good protected membrane roof assembly. And that's because the waterproofing, the thing that actually is doing the lion's share of the work that makes a roof, keeping water out, is protected from damage. It's protected from UV. It's down there safe on the warm side of the building. In addition, oftentimes that waterproofing is a fluid applied membrane. And when you put a fluid applied membrane and adhere it completely to concrete, it ends up being exceptionally durable. As a result of these facts, you tend to get fewer leaks in general in these sorts of roofs. The most obvious one is that even if there was a sizable hole in the waterproofing, immediately below it might be concrete. And if this assembly is fully adhered, like most fluid applieds would be, then that water can't just rush into the building like it would on a conventional compact roof with, TPO and polyiso beneath it. As a result, even it's very forgiving of installation errors. In addition, if there are leaks, which can happen, they're inventing new idiots every day. When there are leaks, they're usually very easy to isolate. So unlike a metal deck system in a compact roof that you might have a leak near a pipe penetration that gets down through the roof and then rides the metal deck, 20, 30 feet somewhere else and then leaks in, with a PMR assembly, the leak, you find where it's dripping down, you go immediately to the other side of the deck, the concrete deck, and that's almost always going to be exactly where the issue is. So it's very easy to isolate. In addition, when leaks do occur, you just need to repair the hole, and that's about it. There's no consequential damage to the roof assembly as a whole. Unlike a compact roof where a hole then leads into the cover board, into the insulation, none of which are supposed to get wet. When you have a sizable leak and you want to repair it, of course, the right thing to do is pull that up, take all the wet materials and replace them and go and patch the roof. You don't need to do that with a PMR because once you patch the hole in the roof, the concrete will dry out naturally by itself, and that's all you need to do. In addition to that, there's no risk of condensation or in the assembly because your waterproofing, which also acts as your air and water barrier, as your air and vapor barrier, that's on the warm side of the insulation. So there's no risk of creating condensation within your roof assembly. Something that happens relatively frequently in compact roof assemblies, particularly roof assemblies that don't include an interior air and vapor barrier or buildings that have higher interior relative humidities. And another great thing that works real well on some of these older roofs, older structures, is that with the right waterproofing assembly, you can install it without slope. So that means that if you have a flat deck, you can go apply the waterproofing right to the concrete, put everything on top, and there's no need for a slope to drain. It's good if you can get it, but it's not always required. And particularly in freezing climates like here, there's some concern about, won't ice cause things to move around? Generally speaking, once water gets through the insulation, it's on the warm side of the building, so there's never an imperative for it to leak or to freeze and then heave or move anything in those joints. So it's a very forgiving system. But of course, there are some drawbacks to PMRs. Otherwise, they'd be used everywhere. The first and probably the biggest is the weight of the ballast. Because it is a ballasted assembly, you need to have some weight on top of everything to keep it in place during wind. Usually that's anywhere between 10 and 13 pounds per square foot. There are some concerns from some people about the risk of the ballast becoming windborne. So a big windstorm picks up little rocks and tosses it over the gravel stop, and then you're paying for a bunch of damaged windshields, for example. There is also a higher cost associated with this assembly. The materials end up being more costly as well as additional labor. I've heard anywhere from about 25% additional to about double. It entirely depends on the roof and the structure and kind of the minutia of it. Then there is the difficulty in making repairs. So when there are repairs necessary in a traditional compact roof, you walk up on the roof, your waterproofing is right there. You see it, you're walking on it. You can find the hole, patch it relatively easy. With a PMR, making those repairs is a little bit more tricky because you need to shovel back the ballast, remove the filter fabric, take out the pieces of insulation, set them aside, remove the drain met, and then you're able to find the waterproofing and the defect in it. But luckily, like I said earlier, it's easier to isolate. But with hospitals, a lot of these things aren't quite as much of a drawback as you might normally expect. Particularly if they have excess structural capacity. A lot of hospitals have planned for future vertical expansion. These are ideal for PMRs because the deck is not sloped and it's got extra structural capacity, and it's a concrete deck almost always, which all three things lead directly to saying a PMR is going to be just the easiest way to go.
Tom, I'm going to stop for one question here.
Yep.
Someone's wondering if you have recommendations for providing containment of high interior humidity environments like swimming pools.
Yes. This particular roof assembly would do very well in that aspect or in that application, but you'd want to be a little bit concerned about chemical interactions of the chlorine. But I mean, if you read the things that Stiburic always talks about, you know, the perfect wall assembly, he goes on in that same article, he talks about the perfect roof, which is the perfect wall on its side, and that's a PMR. So this is what building scientists call the perfect roof, these PMRs. And particularly in those high humidity environments, you really want to do everything you can to contain that air and moisture vapor, and this is the way to go when you've got these sorts of buildings. It's a no-brainer. There's also a question about the risk of ballast becoming windborne. Now there's a design guidance that dictates what you're allowed to do at what height, and you know there's an importance factor attached to that for higher risk or higher importance structures such as hospitals. But generally speaking, when you're able to get a parapet, or if your aggregate is large in general, so more than 1.5 inches in diameter, what I think is called number 2 gravel, then that really minimizes the risk of any sort of windborne ballast. Higher costs, while a lot of buildings that are built, they're by developers who might be looking to flip a building, particularly in residential construction and certainly in some commercial applications. That is not the case with many healthcare facilities. The owner remains the owner for years and years and years and years, and they absolutely get the benefit of these longer lifespans with these PMR systems. As far as the more difficult to isolate and make repairs, that is true, but it's a trade-off between more difficult to make repairs, but you have less repairs to make. Now, I just want to take a moment here and just kind of draw a parallel. I don't know how many of you have heard the car buying advice that, oh, what you want to do is you want to go to your mechanic and ask them what car do they never see in their shop, and go and buy that car because that's the most reliable car. That's what PMRs are to building enclosure consultants. I can't recall a single project where I was called onto an inverted roof membrane or a PMR and they had a problem that was related to the PMR. These are very robust systems, and it's shocking to me that we don't use them more often. And there's a little bit of an extension to that. Green roofs. I've seen them around here where they basically take a traditional compact roof, so PVC, EPDM, TPO, over polyiso over the deck, and then they just throw, green roof trays, soil trays on top of that. And it's just almost without exception, just a bad idea. Please stop doing this. Use PMRs on green roofs. That's what they are just best suited for. This right here is a green roof that we excavated, and there were some leaks, and it's not old. And this is a multi-ply built-up asphalt roof. You can see that they used XPS insulation. They adhered everything down in asphalt, and the roof was absolutely saturated because these green roofs, they have such poor drainage that any defect in the roof just allows water to just fill in the insulation void space, the reservoir that exists beneath these roofs. This roof right here was, I think, 4 years old. This is just recently, a couple weeks ago. We made an opening, and the cover board right beneath the membrane was saturated everywhere. It's hard to find a green roof over a traditional compact roof assembly that isn't having water problems, just because a green roof is very unforgiving of installation errors, and unfortunately, these sorts of compact roofs are not particularly robust. So I want to move on to something a little bit different. This is when you don't have the option to do a PMR, but you oftentimes are stuck with tapered insulation. Now, here in Indiana, we have some very old energy codes. This is back from 2007. ASHRAE 90.1, and our code here says that you need to have a minimum of an R20 of continuous roof insulation everywhere. So it doesn't matter about slope, you have to have basically 4 inches of polyiso everywhere. And if you don't want to do that, then they say, all right, well, you can do the U factor alternative, which basically says, prove to me that your insulation assembly is just as energy efficient as if you put down 4 inches of polyiso. And if you can do that, then we're fine. So what that means is that a lot of designers, they don't know how to do the U factor approach because it's frankly, it's complicated. It's literally multivariable calculus. And they'll say, all right, well, it's an existing deck, or we can't get slope for whatever reason, so we're going to put down 4 inches of polyiso and put tapered insulation on top of that to get slope to drain that's necessary. Well, of course, that can be a big problem. If you've got a flat deck, you've got these runs, sometimes 30 feet or more, which means that at the ridge, you've built up to almost a foot worth of insulation. That's basically just fill. So surely there's a way to reduce our costs here, cut out some material, cut out some labor, and drive the cost of this roof down if we're stuck with a flat deck. So all right, so let's try this U factor route. But how in the world are we supposed to determine the U factor of an undulating roof where the thickness of the insulation varies from point to point to point? Well, let's take an example of this roof right here. It's very simple, 2 drains, slopes north to south with counter sloping crickets in the middle. Now, the way how they install this is they first install what's known as the field taper insulation, which just slopes north to south. And those are the horizontal lines. Those are the board joints of the horizontal lines. And then on top of that, they add counter sloping crickets to redirect water to the drains. So to pull out, this is an exaggerated view of what that slope might look like, how they install the field insulation and the counter sloping crickets. Now, if we're going to take this U factor approach, then we need to find the energy loss throughout the roof. And the energy loss is inversely proportional to the thickness of the insulation. So to kind of graphically show what that would look like, it would look like this, where most of the energy lost is right around the drains, where the insulation is the thinnest. And it is this value that we need to calculate and then average over the surface of the roof. Now, I'm sure that people have been around the block a couple times will say, well, why in the world would I do that? I just get tapered shop drawings, right? And these tapered shop drawings, they lay it all out. They show you where all the crickets are. It's all planned by, it's delegated design. And they provide an average R value. So unfortunately, I did a lot of research into this. And all the manufacturers, all the big roofing manufacturers that provide tapered insulation, they all use the same computer program. It's called Tapered Plus. And I got my hands on that copy, and I talked with the people there, and they are flat out not calculating this value correctly. It says so on their website. They explain how they calculate it, and the way how they do it is they're not looking at the energy loss. They're looking at the total volume of material insulation that they're putting on the roof, and they find an average thickness, which is not the same. So we went through, we did the math, we did the calculus to do it, and this particular roof, which was reported as an R21, actually only had an R17, which means that they inflated the value of the insulation, the usefulness of this information, by as much as 34%. And this is not uncommon. I checked this against a number of others, and without exception, they're over-reporting the amount. And the really frustrating thing is I bring this up to them, and they are just disinterested, near as I can tell, in correcting their programming. They've been using the same one since the 90s, and it's worked well enough so far, so they don't want to mess with it. It's frustrating. And this is a problem, because if you're a mechanical engineer and you're designing and sizing the mechanical systems on this building, you're counting on only so much amount of energy being lost through the roof, or so much heat energy coming in through the roof or the sun. And you could very easily find out that all of a sudden your mechanical systems are undersized because too much energy is being lost or gained through your roof. Moving on to building expansion joints. Now, this is also known as building seismic joints. And at least around here, outside of earthquake country, you only see them at hospitals and in dense downtown areas with zero property line conditions. And what happens is, you've got an existing building and they want to add on to and expand, so they build the building right next to it. And at some point, the structural engineer is going to look into it and say, I don't want to tie into the structure of the adjacent building. I want my structure to be its own thing. So they build them right next to each other, and in the gap, they put an expansion joint. So that's that kind of lighter whitish thing right next to the brick. That's the expansion joint. So we were called to this project because leaks at this condition. And as part of our investigation, we had them demo out just a little bit of brick. This is just above a relieving angle in the brick veneer. You can even see the pea gravel and rope wick that we had to kind of scoop out of there. And the expansion joint, you can see a sliver of it on the right. And we took a tape measure and were able to jam it into that joint, into the building, 9 feet. So there is no connection between the waterproofing of the existing building and the waterproofing of the new building. And that was the principal cause of leaks at this location. And unfortunately, this is pretty common. This is another example. That's a piece of string that I'm holding up to the opening, and conditioned air was just pouring out of this opening. And that can cause all sorts of problems. The energy costs aside, which usually are frankly not that big a deal, it's more an issue of condensation. If you have this warm conditioned air that's now being expelled through the insulation and everything, then that moisture can accumulate and cause mold and all sorts of other bad things to happen in the wall assembly that could go unnoticed for years. Unfortunately, this is something that designers have not always had the best handle on. So this is a building that I worked on. There's an existing building on the bottom part of the screen. This, by the way, is a plan view. And the new building is kind of up on the top part of the detail. And you can see that the waterproofing on the wall just kind of stops at the building corner. So there's nothing preventing water or air or rats or whatever from coming through that brick, through the weeps, and just turning the corner where the building ends, just doing an end run on the air and water barrier, and leaks to the inside. And you might say, oh, okay, well, what they really ought to do is take that wall all the way to the existing wall and seal it there, turn that weather barrier onto the existing structure and make a seal there. Well, there's still a problem. That existing building is itself a veneer. So even if they took that waterproofing all the way to the face of the existing building, there's still a path for air and water to bypass these expansion joints. Now here, this is done by an architect that I have a lot of respect for. They do good work in general, but these are expansion joints, and expansion joints are tough. Here you can see that they've got the new building on the bottom left, an existing building on the right, and they've taken their roofing up onto the existing building, and they're going to demo some of the existing building's brick to tie in the water barrier from one assembly to the other so that they don't get water coming down between the two buildings. But unfortunately, you can see that sheet metal that they've put in that cavity, that's not sealed. So as a result, there's an air leakage path through that sheet metal lap joint. And that interior air, that moisture-laden air, is able to exit the building. And as it's going through, as it's leaving, because of the stack effect, it's depositing its moisture in the wall assembly as condensation when it touches a cold surface, those sheet metal surfaces, for example. And then that drips back to the inside. And even if that joint was sealed, there's still another gap beneath that metal flashing. So this is, once again, a good architect. They know what they're doing, but these joints are tricky. And it's no wonder, really. I mean, these expansion joints have to do the most awkward they have to go through the most complex sort of joints in order to make a seal. So, I mean, here we're just in this one detail, which thankfully they showed. I mean, you can see that it's dealing with a coping, it's dealing with a new brick wall, an existing brick wall, you've got sheet metal tying into roofing. These are a lot of different components with a lot of different trades that all have to work together. So you can understand why the expansion joint, getting that properly coordinated with all these different people, could be a really tough thing to do. So what we've done in the past, and has worked quite well for us, is we use a neoprene bellows. So this is a flexible sheet of neoprene that bridges from air barrier to air barrier. This is one of our details that we did for hospital that I showed that we were able to stick the tape measure in 9 feet. We like using neoprene because it's one of these sheet flashings that's chemically very inert. It plays well with a lot of other materials, asphalts and TPOs and PVCs. It generally doesn't chemically attack anything else, which is really critical when you're trying to create continuity of an expansion joint that's going to be tying in so many different assemblies. So then after you tie in the air barrier from one to the other with this neoprene bellows, then you reinstall the cladding and provide some sort of sheet metal decorative cover that's basically there to cover the joint and maybe shed some water. And this is what it looks like during the repairs. So they ripped out the brick all through there. The shelf angles were also quite tricky, but you can see the termination bar with the neoprene that's attached to one of the studs going up. That was all tied in and sealed off real well. And up at the top, you often have these really horrendous surfaces that you need to seal to. So this is also an area where neoprene is much better. It's flexible, it's stretchy, and you're able to conform these materials to these very unforgiving and unsympathetic surfaces. You know, here we've got the coping, we've got an existing wall, we've got a shelving, we've got the roofing, and the neoprene needs to make a seal to absolutely everything. And now I want to take a moment and talk about moisture vapor diffusion. I'm a building enclosure consultant, which means that I have to deal with building science a lot. And building science is the study of how buildings manage moisture. And moisture vapor was always really tricky for me. I was able to, do the dew point analysis. I was able to use the programs to understand, to see what worked and what didn't. But I always had real trouble visualizing what the heck was happening and kind of understanding the different little facets about it. So after dealing with it and thinking about it for a really long time, I finally settled on a way to explain this to others in a way that might make a little bit more intuitive sense. And I built this little acrylic trough here. And this little acrylic trough is supposed to mimic how moisture vapor flows through a wall assembly. On the left of this picture of that trough, that's supposed to be representative of the exterior air during the winter. There's very little moisture in the air. And on the right, that's the interior, where it's warmer and there's much more moisture in the air. And that moisture on the interior has to diffuse through multiple different layers of the wall assembly before it's able to reach the exterior. And I recreated those by taking these acrylic partitions, and I drilled 40 holes in each of them. And the holes, you can kind of think of that as the material's perm rating. So it's as if we have 5 layers of materials between the inside and the outside. Each material has a perm rating of 40. And as a result, you can see how as you get further outside the wall, there's less and less and less moisture because each one of those layers is resisting the flow of moisture through it. And if you have a material that is a little bit more resistant to moisture vapor, then you can see that it slows up and water kind of backs up behind that partition on the inside as it's trying to flow out. So it's wetter, for lack of a better term, on the right than it is on the left. Now keep in mind, throughout all this, water is still flowing through. I replaced the 5 perm material with something with less than 1 perm. So less than 1 hole is covered up. So, it's actually just a sheet of the transparency plastic that doesn't make a perfect seal, but makes a pretty good seal. And here you can see how water on the right side is very well contained in there. But once water gets through that last partition, it's a free shot out to the exterior. There's almost no water flow through this assembly. So let's look at what this would look like in a somewhat typical healthcare wall assembly, where on the exterior, you've got the exterior air, some sort of cladding. In this case, I'm using a brick veneer, an airspace, mineral wool insulation, a vapor permeable water barrier. Then you've got your exterior sheathing. And you'll notice that there's a space in the middle. That's just a byproduct of how I built the trough. There's not actually a space between the waterproofing and the sheathing. So at this point, just kind of shows how much water is between the two. Then you've got the batt insulation in the stud spaces and the interior sheathing with the interior air right there. Now you'll also notice that there is this red line that I've drawn over top. This is the temperature profile through the wall assembly, meaning that during the winter, it's relatively warm on the inside, say 7 degrees, and on the outside, it's cold, 10 degrees, 0 degrees, it's cold. And as you move through the wall, as you move through the insulation, the temperature drops. So there are 2 layers of insulation, the temperature drops across the 2 layers of insulation, and that's how we get our temperature profile. Now, the water level in this case is representative of the dew point. So as water vapor moves from high vapor pressure to low vapor pressure, interior to exterior during the wintertime, it's going to get blocked at different levels. In this case, the most vapor retarding surface is probably going to be the brick itself. And you'll see that kind of slows down the flow of moisture out of the assembly. And what you want to look for is whenever the temperature drops below the dew point. So whenever the red line drops below the blue line. So you might be looking at this and say, wait a minute, didn't you just say that this was a relatively typical application around here? Well, how can that be if this is saying that you're likely to get condensation? Well, for one, it's a model, so it's not perfect. But more importantly, I think that to a degree that is true. This sort of wall assembly will get some amount of condensation in the wintertime during extreme weather around here. Now, if it's not cold enough or it's not cold enough for long enough, it may not be a problem. These wall assemblies do have the ability to absorb a little bit of water and release it during the warmer months. So it may be that this amount of condensation is not a problem, but that's a risk. So what we often recommend is that you install an interior vapor retarder, which is what we did in this little model. And you can see how that drastically changes the moisture profile in this wall. Same wall, same component, same everything. except for now we've got that interior vapor retarder. And now everything outside of that is just very, very, very dry. So this would be like polyethylene sheeting that you put up inboard of the bat insulation or foil-faced bat. And you see how with this assembly, there's basically no risk of condensation. And of course, we all know that you don't want to put a vapor barrier outboard of your insulation. So in areas where you might get condensation on the cold side during winter, even though I've still retained a vapor barrier. Now, it's not a very good vapor barrier. It's only got about 5 perms, whereas my vapor barrier waterproofing is somewhere less than 2. But even so, you'll see that the blue water is above the red line, so condensation is possible, and that can be an issue. Now, you've probably also heard that it's a bad idea to have 2 vapor barriers in a wall. And let's look at that real quick. So here I've covered up the holes, and I've added essentially 2 vapor barriers, and I've blocked up most of the holes. And you see there that, wait a minute, what's wrong with this? The water level is well below the red line. So what's the matter? It seems like it works great here. Well, here's the issue, is that this is an idealized scenario, and that vapor barrier waterproofing that we've applied to the sheathing is not always going to be perfect. Inevitably, there's going to be some place where water is able to leak beyond that membrane. And when that happens, that water is stuck there and it just builds up. So when the leak gets in, it might want to try to dry to the exterior, but because you've got 2 vapor barriers, that exit path is blocked off, and you end up with increasingly elevated moisture in that area, which leads to mold and rot and rust and all sorts of other bad problems. So I hope you understand a little bit better about how moisture diffuses through walls in a little bit more of a more intuitive way. But I'm going to completely undercut what I just said to talk about how moisture vapor diffusion doesn't actually tend to be that big of a deal. Now, there's an old kind of adage from building enclosure people who say that when they get called to a project, 99 times out of 100, when there's a water problem, it's a water leak. There's a hole somewhere in the building that's letting rainwater in, and that rainwater is causing problems. And the one time when it's not a water leak, it's usually an air leak. So there's still a hole in the building enclosure that's letting warm, moisture-laden air through the wall, through the insulation, where it condenses and that water drips in and causes some problems. But in the one time out of 100 where it's not an air leak, only then is it a moisture vapor diffusion issue. And that bears out with my experience and those that I've talked to, with the only exception being floor coatings, which if you're sticking around for the next one, you should learn about, because those are situations where very minuscule amounts of water can cause much bigger problems. The issue here is that moisture vapor diffusion is not a particularly efficient method of bulk water transport. So what do I mean by that? Well, let's do a little quick thought experiment. Let's take a metal deck and put 3 holes in it, 3 number 10 screw holes. And at one of them, let's fill up water in the flute with a 1/4 inch of standing water. And that water is then going to drain through that number 10 screw hole. And if I were to put a bucket underneath and time how long it took to collect a gallon of water, I would find it would take about 11 minutes to fill up that bucket of water. Now, if through a similar screw hole, I were to allow water or allow air to leak through that screw hole into the roof assembly with a very small differential pressure, just 10 Pascal, which, by the way, is about a 1/4 inch of water pressure difference. 70 degrees, 30% relative humidity. So very kind of typical moisture conditions in a commercial office space. And I were to time how long it took to collect a gallon of water from the water that condensed out of that air leaks, it would take about 11 days for me to collect a gallon worth of water. Similarly, if I then took that same number 10 screw hole, covered it with an air barrier that was completely vapor permeable, so moisture vapor could diffuse through it all day, no problem. Same differential pressure, differential vapor pressure pushing through that, and I were to collect all the water that condensed just from the diffusion, it would take about 300 years to get a gallon worth of water. The point here is that moisture vapor diffusion is by itself not a good method of bulk water transport. Usually when there's water problems, it's air, it's water, with the only kind of exceptions being floor coatings, and it can make a water leak worse if you're trapping it between two vapor barriers. So moving on to storefront windows. This is an area that unfortunately I've seen a lot of designers struggle with how to flash them in a way that is particularly robust. Now there's an ASTM standard, ASTM E2112, that talks all about window flashings. And they talk specifically about storefront windows. These are aluminum framed storefront windows. And they say that these windows, they come to 7 points, 6 of which deal with the sill pan flashing and 1 of which deals with an air seal. They say that you should be used under all windows and doors, form a 3-sided pan, collect and drain water to the exterior, be integrated with the surrounding flashings, be sloped to drain, not be punctured by window fasteners, and provide an air seal. I'm only going to talk about 5 of these real quick. Now, the first is that the sill pan should collect and drain water to the exterior. So what we see a lot of is designs where you've got this sheet metal Z flashing underneath a storefront window. Now, this can be a problem because once the storefront window gets installed, they caulk the perimeter. And that caulk joint goes from the window sill to the pan, which means this 3-sided pan now becomes a 4-sided bucket. And if you're lucky, what'll happen is the water gets in there, sits, and causes that outer sealant joint to fail, and the water is able to drain back out to the exterior after it destroys that outer sealant joint. Oftentimes, we're not that lucky. Water can sometimes just build up in the sill pan and leak to the interior. This is also not particularly common. It's difficult to get that much water around these windows. But what is very common is that water begins to fill those pans, and then it sits there, and it corrodes the pans, and it eats away at the seals until it eventually leaks into the interior in some other subtle way. And once it gets to that point, there's no replacing the sill flashing. It's very difficult. They also say that you want to provide a sill pan under all the windows, and that sill pan should be integrated into the surrounding flashings. So on a lot of projects where we have storefront windows, the designer will show some sort of flashing beneath the window, and then it inevitably gets in the hands of the glazer who VEs out the sill pan. He says, oh, no, don't worry. We have got a sub-sill. It's from the window manufacturer. It's warranted. It collects all the water and drains out. It's great. It's super well sealed, blah, blah, blah. Well, the problem is that sub-sill, or sill can as it's sometimes called, is only designed to manage the water that leaks in through the window itself. It's not designed to take the water from the surrounding walls. So this is a project where we had storefront windows installed with sub-sills because the sill flashing was VE'd out, and we've removed the window. And this is effectively what water that penetrates the cladding sees. It just sees a big old hole. There's nothing preventing water that gets through the brick from just turning in at the jambs and leaking to the interior, which is exactly what happened in a number of different locations. What we like to do is, this is a little bit difficult to see, but if you can see my mouse, this right here is a sheet metal back dam, little L, that gets screwed down there, and then we use membrane, sheet membrane, to form a pan. And this works really well because you want a sill pan that also integrates with the surrounding flashings. Well, this is very easy because the pan is the surrounding flashings, so it integrates perfectly. And they also say that you don't want to puncture the sill pan with any sort of fasteners. So now this is really tricky because every single window needs to be secured in the rough opening. And that means that there's going to be some manner of fastener that has to go down through the sill of the rough opening. Now, some other kind of better ways of doing this aside, the more common way is just a fastener down through the center. But that fastener punctures our sill pan. And because it's beneath the window, there's no accessing it to seal it or detail around it. So it's just a hole, and those holes leak. Now, they do seal the fastener penetration in the subsill, but not where it penetrates the sill pan. You can see that a little bit more clearly in this. Here we've got the subsill installed on top of the sill pan right here, and you can even see the membrane beneath that. And they only seal at the topmost layer. Now, one thing that these people will say is, oh, no, it's all right. When we drill through the subsill, we take our caulk gun and we squirt caulk into those holes, and that seals it up. Well, this is what it looks like after they pre-drill these holes. And these, if you're going to inject seal into that, you're going to have to contend with all the stuff that the pre-drilling brought out. And this is just what came all the way out to the exterior. There's no cleaning the area on the level of the pan off. So I actually, to show this a little bit more clearly, I built an acrylic storefront window, made entirely out of acrylic, and put it into a little wooden wall with my helper there. And you can see that after I pre-drilled the subsill, you can see the white bit, that's the acrylic, that would be akin to the aluminum shavings that come from pre-drilling. But there's all that wood beneath that also came up during the pre-drilling. And if I inject sealant into that, I'm not sealing at the membrane, I'm sealing to sawdust. So what we recommend is after they lay out their subsill, clamp everything down, drop their fasteners in, they take everything out to expose the pan. And now they can see where they've actually punctured the holes in the sill. And they can then take a rectangular shim, a plastic shim with a pre-drilled hole, which are easy to make, set each one of those in a little bed of sealant, and then reinstall the subsill. And you can see here, this is the subsill, there's that plastic shim. The sealant has bubbled out where it got compressed by when they tightened down that fastener. And there's still room for them to use horseshoe shims to level out their window. So it's still adjustable. But in doing this, they create a really spectacular seal around each one of those fastener penetrations. And it works out really well. And the last thing related to storefront windows is providing an air seal that doesn't block drainage. So if you want it to block drainage, it almost by definition has to be on the inside, an interior air seal as it's called. And the reason for this is not that we care about a draft. No, what we care about is what the air can pull in with it. So this was a mock-up where we tested initially without differential pressure, so just spraying water on the outside, and this curtain wall did not leak. It wasn't until we started sucking air from the inside to create a differential pressure that we actually started seeing leaks. And you can see the air on the bubble that is drawn in right there. So we're worried about air pulling water in. And this is a real scenario where a window that not a nail fin, so it's storefront-ish. We tested it without differential pressure, didn't find leaks, but this particular project had some pretty severe storms come out of the west, and when there was wind-driven rain, there was air leaks around these windows, which caused the water to be sucked up by the drywall that was poking in at the rough openings because there wasn't an air seal. And now on to the last point that I want to make, and it's related to sheet metal flashings and sealants. I hope at the end of this, you guys will realize that sheet metal flashings and sealants should not be relied on as waterproofing. They should be water shedding elements. So let's first start with sheet metal. Sheet metal does not come in infinitely long lengths, so invariably you're going to end up with splice joints. And splice joints are the big weakness in sheet metal flashings. If we were to do a cross section through that splice joint, you would see two pieces of metal with a bit of sealant inside. Now, I'm being very generous here in saying that that bit of sealant is a 1/16 of an inch thick. And I'm also assuming that it is installed perfectly, which of course it is not. But let's pretend for a moment that's a urethane sealant, even though no one in their right mind would use urethane. And just look at the geometry of this. If a urethane can be expanded or stretched an additional 25%, then that means that as these bits of sheet metal expand and contract with temperature that just naturally fluctuates from winter to summer, you would expect the sealant to fail with enough of a temperature swing. So applying numbers to this, if you get a temperature swing that induces this much movement in the sheet metal, you would expect the sealant to fail. Even a perfectly installed sealant joint, you would expect it to fail. So using urethane sealants with these different materials, it doesn't take a big temperature swing before you would expect these sealants to fail. Now, you might be saying, okay, well, this is urethane sealant. Silicone stretches more, so how does that change it? Well, it's still not very good. I mean, it's less than 100 degrees for any sort of lap joint, meaning that anything that's exposed to the sun between winter and summer, there's a good chance that that's going to fail. You would expect it to fail even when perfectly installed. Splice plates, traditional lap joint, that can make a big difference because it essentially doubles the temperature swing by halving the length. But once again, we're relying on a perfect install, which is not, in my opinion, reasonable. And there is also the use of butyl sealants, but that has its own problems about staying where it's supposed to and not getting kind of weathered out and stripped out of the joint because it never fully cures. And that takes us on a little bit further to just sealants in general. And too often I have seen sealants fail for all sorts of different reasons. And one of the big ones is poor adhesion. So this right here is a chart that published by Dow Corning, who makes only silicone sealants, and it has recommended surface preparations for these various substrates on the left. And the substrates on the left, they're all kind of, hard, flat things. Different coatings on aluminum itself, copper, steel, plastics, hard, flat things. But these silicone sealants, you can't see a rhyme or reason to when a primer is needed or not, whether it can go on normal or not. And this is a big issue. If you don't get it tested before you install it, you could end up with all your sealant joints fail. And it's not uncommon that I've been to a project and found that, oh yeah, no, the perimeter window seals have all failed 100% because they didn't do this testing. And what's really annoying, this testing is free. You send a sample of the waterproofing or the metal that you want to seal to the manufacturer. You say, hey, I want to use your XYZ sealant. What do I need to do to prepare this surface? They take it, they test it, and they send you a nice report saying, solvent wipe or use this primer or whatever. And there you've got the data for what you need moving forward. You just need to do it beforehand. Now, this is incredibly common. So this, for example, was a window that wasn't properly primed. This was a sealant that was applied to a dirty brick. This is a sealant that was applied to an oily residue on this curtain wall. This sealant was applied too thick. This sealant was applied too thin. This sealant was over-applied and caused that sealant to fail. This sealant was attacked by birds because they like the feeling of it in their beaks. This sealant was applied too thick and without the right primer. This sealant was a multi-component sealant that was poorly mixed and stained these joints. This sealant was applied without the right primer, and this sealant was also applied without the right primer. All these photos are from a single project. This is so common. We have to stop relying on sealant as a method of waterproofing because it is just not reliable enough. Facilities, I'm kind of painting a doom and gloom scenario here, and I apologize for that. And you're probably also noticing that, well, it's not that bad. Well, the truth is, no, it's not. But thankfully, that's because of the people who work there. To a lot of you guys who are, if you're working on a healthcare facility, you tend to be on the top of your game. So you don't make a lot of the mistakes that some other people might make on other less important buildings. Specifically, like the mechanical engineers, even when there is an issue, phenomenal engineers that are able to pressurize this building, dry out this area, apply new registers that prevent condensation, that very good mechanical engineers. In addition to that, the maintenance regimens on all these facilities is usually very deliberate and planned out over years, whereas on other buildings, it's only call me when there's a leak. Only the squeaky wheel gets the grease. But of course, healthcare facilities are among the most demanding facilities out there. And currently, building enclosures are hard. The industry as a whole has not really stepped up to the plate as much as we could to provide the type of buildings that are necessary in these critical facilities. And hopefully, in listening to this, you all have learned something, and you can take this onto your next project so that we can, keep raising the bar and doing better for our clients and for the people in these healthcare facilities. So thank you very much. I'm going to open up for questions. Of course, for those of you who joined late, for your CEUs, please contact Kristen Zerlag at that email address, and she can get you a CEU for this.
All right. If there's no more questions, well done, Tom. Great presentation. Thank you to our attendees for joining us today. Like Tom says, email kristen.zerlag@sme-usa.com for your CEU cert. And we hope to see you at our next session that starts in a couple minutes here. We have Haider Al-Halal and Shane Giordano presenting on lessons learned floor covering failures. Thank you so much for joining.
It's a good presentation. You all should watch it.
It's really good. Thank you again.